I bet you already heard about hierarchical models, or multilevel models, or varying effects models. Yeah, this type of models has a lot of names. Many people even turn to Bayesian tools to build exactly these models. But what are they? How do you build and use a hierarchical model? What are the tricks and classical traps? And even more important, how do you interpret a hierarchical model? In this episode, Thomas Wiecki will come to the rescue and explain what multi-level models are, how to build them, what their powers are, but also why you should be very careful when building them. Does the name Thomas Wiecki ring a bell? Yeah, probably, because he's the host and creator of the PyData Deep Dive Podcast, where he interviews open source contributors from the Python and data science worlds. Thomas is also the VP of Data Science at Quantopian, a crowdsourced quantitative investment firm that encourages people everywhere to write investment algorithms. Finally, Thomas is a longtime Bayesian and core developer of PyMC3, a fantastic Python package to do probabilistic programming in Python. On his blog, he publishes tutorial articles and explores new ideas, such as Bayesian deep learning, for instance. And Thomas cares a lot about open source software sustainability, so he puts all he's up to on his Patreon page that you'll find in the show notes. This is Learning Bayesian Statistics, episode 11, recorded February 2, 2020. Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the project, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country, and reach a true Bayesian state of mind by visiting learnbayesstats.anvil.app. That's learnbayesstats.anvil.app.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly I'm watching eyes.
Thomas Wiecki, welcome to Learning Bayesian Statistics.
Thank you very much for having me. I'm excited to be here.
Yeah, thank you for taking the time. I'm really happy to have you on the show. I remember your blog was one of the first resources I used when I started learning Bayes stats.
Well, that's very cool to hear. Yeah, I'm really positively surprised by the reach that blog has. It keeps coming back to me in all kinds of ways.
Yeah, that doesn't surprise me because you've got a really nice content over there and kind of evergreen. It doesn't get outdated very quickly, at least.
That's very kind of you to say.
Yeah, I know. You can reference it quite easily. Just sometimes the version of PyMC changes or stuff like that, but the statistical theory behind it doesn't change every year, so it's okay.
That's right, yeah. It's a timeless quality to it.
Yeah, exactly. I remember it was very useful to learn hierarchical models. So that's what we'll focus on today. But first, I think it's better to start by your background. As you put it, before you were doing brain stuff. And if I understood correctly, you did your PhD in computational psychiatry. So what's the story behind that? Why did you start there?
Right, yeah. So going back all the way, I started getting into computer stuff when I was about 10 years old. My brother had an Amiga, which was like the coolest computer. It still has a warm place in my heart. And so I would just play games, but eventually those would get boring and I would start programming in Amiga Basic. I'm still very fond of that programming language just because it's the first one I ever toyed around with. And that really got me hooked on the whole programming and making computers do things and solve problems. I always was interested in science and really also how you can use computers to solve difficult problems in other domains. So then when I finished high school and I thought about what I would study, I wondered how could I best combine these two passions I had. And at that time, bioinformatics was like the hot buzzword. Everyone was predicting that was going to be the sexiest job of the 21st century. Turns out they weren't completely right with that, but maybe close enough. And so that just became a natural choice. So I moved to Tübingen, Germany, which is a great university, and started studying bioinformatics. And there are different focal areas. One of them was neuroscience. I mean, what's cooler than the brain? Not many things, if you ask me at least. And so I really got into neuroscience, and also they had the Max Planck Institute there, which is now called Intelligent Systems. They are doing really amazing research on neuroscience, but also how that relates to computer vision and machine learning in general. So I started working there part-time. And so really neuroscience was just something I was deeply interested in, and it connected so nicely with computer science and machine learning statistics. And that really made it an obvious choice that when I met Michael Frank, who became my PhD supervisor at Brown University, to move there and study neural network models of the brain, specifically a part of the brain called the basal ganglia, which is old structure related to reinforcement learning. And what is really interesting about that structure is, well, we understand it pretty well, but also it's related to all kinds of psychiatric diseases and neurological diseases like Parkinson's disease. And that was just inherently meaningful to me to work on these types of problems that had a real-world impact. The combination of computational modeling to solve these problems in psychiatry is then called computational psychiatry, which was also and still is a new field in neuroscience and psychology that tries to answer these really difficult problems. And that is what I did my PhD on. It was a very nice combination of like all these passions coming together.
Yeah, that's very interesting to hear about. Yeah, you really thought about how to combine your different interests and passions into your work.
Yes, yeah, absolutely.
Yeah, that's great. Nowadays, you're still working on applied topics, but I think you're in finance, right?
That's correct. Yeah, quant finance.
The common thing I see between these different activities is Python and Bayesian statistics. So do you remember how you first got introduced to Python and Bayesian methods? And also, why did they stay with you until now?
The way I would phrase it is that these are probably my favorite tools and I find them very powerful, but for me, it's never really been about the tools, but about solving problems with whatever tools are good for the job. It just happens that I'm very well versed in them, and that makes them an easy choice for me to use. But so, yeah, with Python, I got started by trying to wean myself off of MATLAB, which was when I was working at the Max Planck Institute. Everyone was using MATLAB, and especially in academia. At that time, was the standard thing. Everyone was using it. And I was pretty happy with it, but I definitely, coming more from a programming background, I could definitely see the limitations of that language or framework. Some early adopters at the Max Planck Institute were already using Python, and we were chatting about it, and I thought that was really interesting, so I just started playing around with it, and then, of course, trying to convince everyone else to use it with mediocre success. And I remember everyone always had to defend Python to MATLAB, where it was like, oh, so can it do this type of plotting? And then the answer would always be like, well, not quite yet, but like Matplotlib is really getting there and it's becoming easier and better. So it was always just trying to catch up, and the year of Python would be around the corner. Of course, now with the perspective we have now, it's really funny to look back and be like, well, what are the things that MATLAB can do that Python can't? And well, there isn't anything, but the other way around, it's shocking. So Python has just been a joy to use, so it's why I stick with it. And Bayesian methods I learned in winter school in Amsterdam with E.J. Wagenmakers. At that point, we were using WinBug, so it was really early days.
Vintage days.
Yeah. The thing that really convinced me was on a certain, like on the 6th day or something of that school, they started talking about hierarchical models. And they had this really cool example. So this was focused on psychology. So there was a memory recognition task, and you would model how fast people would forget some items you told them with an exponential decay function. And there were missing data points in there. But there was also one subject where you just lost all the data altogether. And because it was a hierarchical model, you could still infer data from that hierarchical prior. So what you learned from the other subjects, you could apply to that missing subject. And I was like, what? That's amazing. I don't even need to collect more subjects. I can just simulate them, which of course is ridiculous. But that really was the point where it clicked for me with Bayesian statistics, with these hierarchical models. And I mean, probably going to talk some more about that. But yeah, that is really where it all came together.
Yeah, I can really relate to that. It was also a very, very nice revelation to me when I first learned about hierarchical models. Yeah, it was really amazing. Yeah, and of course, we're going to talk about that more in detail later in the episode. But just to talk a bit more about the link with finance, I know Python is more and more used in finance, as I worked in finance too for a while. But what about Bayesian stats? What proportion of models are Bayesian at Quantopian, for instance, if you can talk about it?
Yeah, absolutely. So in general, in quant finance, it's hard to say what people use because the field is so secretive. But I do know that there are definitely people at these hedge funds that are PyMC 3 users. How widespread that is and how many of their models are using it, I can't say. My feeling is that it's probably the same in a lot of domains where data science is being applied more and more in. There are some early adopters who use probabilistic programming based on statistics, but it's not really penetrated too deeply into any of those fields. So I think that will just take more time and more communication and teaching of these methods. But yeah, I think there's a lot to be gained by quant finance in general in all these domains. And definitely we've proven that at Quantopian for ourselves. The model that really made a big difference for us. So our investment process changed a lot over the years, but at one point the way we structured the fund was that we would have the crowd. So we have this platform, right, where people come onto the platform and they have all the tools. They have a Jupyter Notebook environment to develop and research trading algorithms. And then we would look through the database and find the best trading algorithms that users have developed, contact them, ask them to license the strategy from them, and then deploy it. Then the question arises, well, which of those strategies should you choose and how do you combine them together? And that turns out to be a really difficult problem because, well, you have the backtest period, so people have access to historical data. Inevitably happens is they overfit on historical data, so you rarely see a backtest that doesn't look great. But then, of course, once it goes out of sample and you try to run it in real time, it often doesn't do as well. So that's the classic overfitting problem. So then the question is, well, how much out of sample do you need to accumulate for there to be enough evidence to say, okay, I'm going to deploy this strategy? And, well, place where you want proper uncertainty quantification, Bayesian statistics is a great tool. And Adrian Zabel has built this incredibly rich and detailed Bayesian model that modeled the return streams and all kinds of properties of these return streams of these trading algorithms. There's a couple of things that you need to take care of, like the volatility in the market is changing, right? 2009, the market crash, volatility spiked a lot, and there's periods of calm, and trading algorithms are affected by that too. So you need to have your model account for these changes in volatility, but then also there would be changes. Sometimes the strategy would work better, sometimes it wouldn't. So you can imagine that if you place parameters and include all that structure, and then, well, that model was also hierarchical. So it ended up having something like 40,000 parameters, which was by far the biggest model that I've ever seen. And to my surprise, it actually worked. So the model would be fit. I never thought that it was even possible to build such large models, but Adrian had more confidence in, well, his skill and also Bayesian statistics than I had. And then we would simulate future returns. So you fit the model, and that doesn't really give you the answer that you're looking for. The result of the model fit would be posterior distributions. But what do you do with those posterior distributions? That only tells you, well, that strategy has 70% probability of being profitable based on the out-of-sample data that I've seen, and this other one has a 75% probability, and this other one has 72%. Then the question is, which of those should you pick? Well, should you just pick the best one? Should you pick all three because you have some hedging of risk if maybe one of them doesn't actually work? So these types of problems are really difficult, and they're not answered by just looking at posterior distributions. So what he used, and which is really the technique that opened the door for me on many kinds of problems, and I think it's really underappreciated currently, is Bayesian decision-making, where you then can simulate future data from the model and then plug that into an optimizer and say, okay, I want the allocation that, for example, minimizes my risk of losing money. That would not only give you the uncertainty quantification of your Bayesian model, but it would also solve the actual decision-making problem that you're working on. So you're not dealing with posterior distributions, but you're dealing with actual decisions that are then the output of this whole pipeline. And that has been really powerful for us in not just informing a decision, but making a decision.
Okay, so it would look like something like a cost function or something like that?
Exactly, yeah. So you have your simulated returns of what the model dreams of what the future might look like. And those are the outcomes that you observe. And then you have that objective function or loss function that tells you, given a certain allocation that I make, how much do I like the outcome of that, given the returns that are simulated by the model? So you link together the outcomes from the simulation and the potential decision that you're making, and that tells you how much do I like that. And then that already defines the optimization problem. So just trying to find the decision that will minimize your loss function.
Yeah, that's very interesting. It really looks amazing.
Yeah, and that can be applied not just in quant finance, but almost every problem. So for me, it's really the missing link between us talking about posterior distributions, which no one understands. I mean, I don't even understand them. And then how could I ask other people who are not Bayesians to understand them, right? So if you try to communicate with other parts of the business, then you need to find a language that everyone understands. And posterior distributions and probabilities are just not the right tool for that. So yeah, Bayesian decision making is that technique that for me solves a lot of those problems.
And do you have an example maybe somewhere where you have this whole pipeline implemented, maybe in a GitHub repo or else that I can link to in the show notes?
So I have a blog post on that pretty recently, which has Bayesian decision-making in the name, and quant finance problem that I just described, but that is trying to optimize a supply chain problem, but using those techniques and introducing every single step. And then this was the last round of talks that I gave. Can also link you to the slides, which go through the whole pipeline.
Yeah, that would be great. We could dive deeper right now, but I think it would take us a lot of time.
There's other interesting things to talk about as well.
Yeah, exactly. But yeah, that's something interesting to link to, and maybe an interesting topic for a whole episode. From what you said just now, I got the feeling that you think that Bayesian methods are appropriate for finance.
Yeah, absolutely. For many reasons. I would actually say it's perfectly suited and probably not utilized enough for how good of a fit it really is. For several reasons. One of them is that just in quant finance, uncertainty is everywhere, right? It's inherently noisy. You never really know what's going on. So you could either shy away from that and be like, well, we can't do anything. But really, the best way forward is to approach that uncertainty head on and try to quantify it. And Bayesian statistics is a very great framework to work with that. And it allows you to incorporate a lot of the structure that we know about markets already, like what I mentioned before, that volatility is indeed changing. That if you have good priors, and we do have them in many cases where just there's expert knowledge about finance, economics has studied this for many decades. So we can include that in the form of priors, and good priors help us tremendously with that problem of just things being noisy and not robust. The other thing, of course, is that the tails really matter. We have these outlier events, and so many of statistics, even if it's maybe not apparent, still has the normality assumption baked in somewhere. So with Bayesian statistics, because it's so transparent, you really can see every part of the model and make sure that you're taking tail risk into account properly. And then, of course, there's other things like time series in general are pretty difficult to model with, say, many machine learning techniques, especially if you don't have good priors on the structure. So the core problem always is non-stationarity. So history doesn't really repeat itself, maybe to some degree, but things are just changing all the time in the market. Being able to incorporate the non-stationarity as well is just something that Bayesian statistics allows to do pretty well. And then also there is this very natural hierarchical structure. So in our case, for example, there were many, many trading algorithms, and we assumed that while they were all different, they definitely shared some similarities. And we could exploit that. There's also just inherent hierarchical structure in the market. So different sectors have a lot of the same properties and are very clustered together in correlation space. Then sectors have industries, and those consist of companies. So everywhere you look there are these hierarchical structures, and incorporating them in your model will also just give you a huge boost in statistical power.
That's actually a very nice segue to hierarchical models. So I think it's the best time right now to dive right into them, which is the core of this episode. I remember that in episode 2, Chris Fonsbeck mentioned that he saw a lot of people turning to Bayes to do these kind of models. So I'm wondering, just basically, how would you define hierarchical models to these people and to our listeners?
I agree with Chris that hierarchical models are the superpower of Bayesian statistics. And really, I don't think they really need to be explained all that much, because we all know hierarchies and they exist everywhere. And I'm sure every data scientist or person listening to this podcast will know that there are nested data structures in their data. So, for example, in psychology, where I started, it was a very natural fit because we have the same behavioral tests that we administer to individual subjects. And again, those individual subjects would all be different, but they would group according to how similar they were. And maybe there's different groups. There's healthy controls, and then there's depressed patients. So those would be two different groupings, but they all shared hierarchical structure. More examples include AdTech. You have multiple categories of items that you want to sell. Again, those have similarities, but also differences, and there's natural hierarchies there. In retail, you have things organized into categories. Politics, you have the country into states and provinces. In real estate, there's a really cool example model that I like, which models the housing prices in New York. And also there you find these hierarchies between boroughs and neighborhoods and certain effects that interlink all these different levels. So hierarchies are everywhere, and it's something that is often not very easy to model with other techniques. And I think Bayesian statistics is just a very natural way of dealing with those. But there are other ones, like frequency statistics has dynamics effects models, but I argue that Bayesian has the best answer for that. Moreover, it's also an area where classic machine learning often struggles because it's hard to incorporate, or said another way, they don't really have a good way of finding these hierarchical structures. Something like a random forest, right? It just would be very difficult for that to identify this type of structure. There are different approaches that make use of that, and I think that that is one of the core reasons why, for example, deep learning has really been so successful. Things like object recognition, because there is a lot of hierarchical structure embedded there too, where lines form simple shapes and shapes form more complex shapes, and then these turn into something that looks like an eye. So if you keep learning these hierarchies, then as demonstrated quite impressively by deep learning, you can solve these very difficult problems. Of course, with deep learning, you need tons of data to bootstrap the whole hierarchical information and extract it. With Bayesian modeling, you can be more targeted and already incorporate this knowledge that you have about hierarchies directly into the model.
Yeah. And well, this idea of hierarchy that you talked about, it's basically that, for instance, to take your example about politics, which is a topic I often study, it would be like, you've got some districts in a city that are different in some way, but that are also similar in some other ways. And so you would add a hierarchy, you would add a level in your model, which would be, for instance, the whole city. And this higher level, the city level, would allow you to model how much different are each counties from each other.
Yeah, exactly. So no matter where you apply it, once you have these hierarchies and you correctly specify them, you get a huge boost in statistical power and robustness. So one way to view hierarchical models is to think of them as a form of smart regularization, where you don't just say, well, I'm going to shrink everything towards zero. You shrink everything towards the group mean, and you learn all of those things simultaneously. So that is, I think, a useful perspective if you're coming more from machine learning background to think about hierarchical models.
Yeah, it's basically also a very clever and kind of automated way to have regression towards the group mean, as you said, because then each county, for instance, to take my example back again, each county would have its own parameters, but these parameters would inform the city level mean, and the city level mean would in turn inform each county level parameters. So it allows you to pull information across counties, and also each county level parameters will be regressed toward the group mean, which allows you to have, as you said, a natural regularization of your parameters.
Yeah, and Nate Silva used exactly those types of models with great success, as we all have seen. So yeah, that just demonstrates the power of that approach.
Yeah, exactly. And you were referencing, for people that don't know, Nate Silver, so the founder of 538.com in the US, which is a website that tries to predict elections and also sports. But I think the predictions are better or more accurate for political elections. And so, yeah, it's very interesting also to see that. Unfortunately, the model is not open source, so we can't really see it. But it's always interesting to see this dependency of each level in the data, as you said. I think that's an interesting part about hierarchical levels. I would encourage listeners to go back to your blog posts about them. You did a 3-part series about them, right? If I remember correctly. And yeah, because we're talking about them right now, but it's always a little drier on a podcast. You can't really dive in really deeply into, well, I don't know which distributions you used and so on. But for people interested, I link to your 3-part series in the show notes. And also Also, there are very good notebooks on the PyMC website. I tend to think, because I really love these models, and I really agree these are very powerful. And I remember being amazed when discovering them, but they are really hard to fit and to interpret. So I think I wouldn't advise beginners to start by these types of models. I wonder what's your take on that?
Yeah, I think I agree with that sentiment. For all the power they have, they can be challenging to fit and reason about. Oftentimes it actually would work fine, but nonetheless, it is, I would say, second tier technique. I would actually not even just say to beginners to not start with hierarchical models. I would say to everyone to start with just the simplest linear model that you can come up with. And then from there, just slowly keep incorporating more and more structure. That is advice that I often give, but rarely keep myself. I always start with like the most amazing model that I can dream up, and then it never works. And then I keep going backwards to the simplest model and start from there, and then things start falling into place. But yeah, one of these days I'll listen to my own advice.
Yeah, actually, your advice is echoing Junpeng Lao's advice in episode 7 to start simple and then build upon that. And I also had Ari Harkitainen, one of the PyStan in RV Score Devs in episode 10, who also said the same thing, that he had the tendency to start with the most difficult model, which was not the good thing to do.
Yeah, it's hard. I mean, you get excited and then you want to...
Yeah, exactly. I do the same thing. But to be more specific, I think one of the biggest difficulties of the hierarchical models is that in the end, when you fit the model, you've got all this hierarchical structure that's modeled, as we said, with the different levels, and that tells you how much different each cluster in the data are compared to the group mean. Also, in the end, how much did each cluster contribute to the group mean? Because the more observation you have in a cluster, the more influential the cluster will be on the group mean. But I think one of the biggest difficulties is that because of that, all the parameters in the models are correlated and interact with each other, which makes choosing priors and fitting the model all the more difficult. So I'd like to focus on these hard parts of hierarchical models, and I wonder what you think they are and how do you usually solve them?
Oh boy, yeah, that's a tricky one. Yeah, these models are somewhat hard to think about, and once you get really down to the nitty-gritty details. One of the core problems of them is already what you touched on is, let's say we have a couple of parameters that we want to estimate, and we assume that those are from the same cluster. And so then we have a cluster mean and a cluster standard deviation. So we assume that the parameters in that cluster are normally distributed around those mean and standard deviation. That is just a very classical hierarchical model. But if you then assume what happens if, let's say, we set the standard deviation of that normal cluster normal distribution to 0, collapses to just the mean, and all the parameters, because there's no wiggle room for them to move, also all collapse to the mean. And that is what I call the funnel of doom, because in there, it's very dense and you can't really get out of it. So everything becomes very, very correlated at that point, or once you approach that point, really. It's very difficult then for the parameter to move out of that or move anywhere, really. That is, I would say, the biggest problem. Fortunately, there is a pretty straightforward solution to that, where you can apply a reparameterization trick to how you specify that hierarchical model. Then those problems often, not always, but often go away, and it makes it much easier for the sampler to explore that posterior.
I'm jumping into your answer a bit because, here the problem that you're talking about, which is basically when higher level sigmas or standard deviations, which is the group standard deviation that gets close to 0. It means that basically learning about one cluster means that you basically know all of the other clusters, because the other clusters are considered very close to each other because the standard deviation is very low. But when you get into that situation, as you said, you've got this funnel of doom, which makes it very difficult for the sampler to sample from the model. And then you would use what's called a non-centered parameterization, which is very uninformative, I think, as a term. And it's actually very well documented into one of your blog posts. And yeah, you're right. It's really amazing when you do that. It usually gets rid of all your divergences.
Yeah, exactly. It's kind of magical. The thing that even when writing that blog post, I wasn't really aware of is the question becomes, well, so great, we have this reparameterization trick. Why don't we just apply that all the time? Like, why even specify hierarchical models in this old way if the non-centered version is just better? But it's not that easy because it depends on the model and it depends on the data. So if you have a lot of data where each parameter in your cluster would be very easy to estimate, then you don't even run into that problem of that funnel because it is clear for the sampler that there's nothing interesting happening if you move into the standard deviation being low. So in other words, you have so much information that you know that the standard deviation is not going to be very small. And then there's no problem most of the time. And however, if you don't have a lot of data, then you run into this problem. So it's dependent on the data. So you can't know ahead of time which parameterization is actually the better one. So even the non-centered version does have problems once you do have a lot of data. So they both have their issues in different cases. And you don't really know which of those is going to be better ahead of time. So that is really, for me, one of the key problems of Bayesian statistics today is that there are all these reparameterization tricks, not just for hierarchical models, but all kinds of models, where you just need to know, really have an intricate understanding of the geometry of your posterior and what is happening in these different scenarios to identify them. Once you identified them, you need to know, well, what mathematical trick can I apply to reparameterize my model? I mean, who even has the skill to do that? Maybe Michael Betancourt, but not me. So these are really difficult problems, and they stand in the way of wider adoption of probabilistic programming. One really interesting approach that Brendan Willett is taking, he has developed or is still developing, it's still early days, but it looks very promising, a package called symbolic PyMC. That is essentially a rule-based framework where he implements all these different reparameterization techniques as rules, and then you give it a model, and automatically it would apply all parameterizations that you can imagine and produce all these types of models. So you would give it a centered model, and it would produce a non-centered reparameterization, or vice versa. And then, of course, there's the question, well, what do you do with those different reparameterizations? In the simplest case, you could sample all of them and just pick the one that has the fewest divergences. There's more clever things you can do too, but nonetheless, having this framework that automatically can produce different reparameterizations of your models, way to automatically pick the best one is, for me, currently the holy grail of solving this last really big problem that a lot of beginners run into. I would say, from my experience, 90% of the models just seem to work fine. But once you get in more difficult territory, those 10% cases where you start having divergences, that can be really difficult to deal with if you're not expert level. And yeah, so symbolic PyMC, I think, has great premise in changing that.
Yeah, I completely agree with you on that. It's true that this project is amazing. I really hope it will be able to do what it set out to do. And I'll link to that also in the show notes. The show notes for this episode are going to be big. But yeah, I think that would be really awesome because, yeah, as you said, you kind of always have to check the centered parameterization, the non-centered one. And here we're only talking about two of them, but there are also other tricks, as you said, algebraic tricks that are really harder to understand and even to be aware of. And so that's basically something that stands in the way of Bayesian adoption. And also you have to keep in mind, I think, that using the non-centered parameterization is always a little harder because then your model is harder to read. And so if you have to share the model and when I explain it, it's always harder to do that with the non-centered parameterization, whereas the centered one is usually easier to understand, I'd say. So yeah, basically, I completely agree with you.
I agree. That is even arguably a limitation of probabilistic programming packages. And with PyMC4, we now have some tricks where you could just specify a hierarchical model, and instead of having to write it in two different ways that look very different in code, you would just specify which parameterizations of the two you want. So yeah, I think there's a lot to be done just in terms of tooling of abstracting those parameterizations away, and then you would just show that model around and people would be able to read, oh, this is a hierarchical prior, I know these types of things, and I don't care what extra parameter you passed in for the parameterization. I don't even understand the parameterization. All I know is it's hierarchical and it works and it samples.
Yeah, exactly. I completely agree. That would be so awesome because in the end, what you care about in your model is like kind of the graphic visualization of your model. So just saying, well, this parameter is the group level parameter. It's following this normal distribution. And then you have the cluster level parameter that are following this normal distribution that depends on the group level distribution. But in the end, you don't care about saying, oh yeah, it's implemented in this way and in that way instead of that one because I couldn't fit it. Keep in mind that this cluster level parameter, its mean depends on the group level parameter, period. You don't care about saying, oh yeah, it's parameterized that way or not, I think.
I agree. And it's important to realize that, for example, the funnel of doom, it's not a problem of the model. The model is completely fine. It's just a problem of the sampler. So it's really just a technicality that we have to circumvent. But the fact that this occurs in the posterior is totally understandable and no problem. It's really just, the sample is not being good enough currently to deal with that type of geometry.
Yeah, I understand. It reminds me of someone asking a question on the PyMC discourse, I think 2 or 3 months ago. And he was asking for some advice because he had the feeling that each time he was trying to do real Bayesian inference, which means in real life with his own data and his own models, he couldn't fit the model. So it only worked in examples and blog posts that he saw and he was trying to reproduce. Then it worked. But then when he was trying to do that with his real data, it wasn't working. So he was asking for some general advice. So it was ringing a bell when you talked about that.
Yeah, the real world is often way messier than what we make it appear in blog posts and books and all that.
Yeah, that's true. Exactly. Because there is like a selection effect in blog posts or books, which is like you only write a book or a blog post about an example that works. And also you don't see all the different versions of the model that the writer tried and didn't work, So you maybe have the feeling that you're not good, you're doing something wrong because it should work from the first round. But actually, it's not supposed to work from the first round. But if you're not aware of that, you can be kind of feeling lost,
Yeah, I really appreciate you making that point. I hadn't realized that for myself as clearly, but yeah, you're completely right. That is something I think we all should communicate more clearly, that this is hard work and iterative work. It's not that you just see a problem and then you build the model that perfectly suits that. But yeah, there's a lot of trial and error that goes into it. And the final model often looks way, way different than what you imagined at first.
Yeah, exactly. Well, just maybe to talk also about another problem, because all the problems from hierarchical models don't always come from parameterization problems. Well, as you said, these problems from parameterization are mostly problems because of the sampler. But I think there are also problems sometimes that are due to the way models are defined by the user. I mean, for instance, not having regularizing enough priors, Most of the time, if you use default priors with a huge sigma on the group level parameter, then you will have divergences. But if you're using regularizing priors and doing prior predictive checks, then you will have a model that fits if you're lucky with your data and with your parameterization, of course. So yeah, I think it's also a very interesting avenue to really think hard about the priors and check them even more for generalized linear models, because you have the distortion because of the link function. I don't know what you think about that.
Yeah, absolutely. That is also a point that I think needs to be made. Michael Betancourt has some really great materials on that too, where he really explains step by step the whole model development process. And part of that is just simulating data, even without having any data, just having the model, simulating data from the model, fitting the model to that simulated data, kind of recover things. And that way you really learn about what is the model capable of producing. And often when you look at that, when you do posterior predictive or prior predictive check like that, you find that it produces, for example, regression lines that are completely unreasonable. You never would expect that in your data. The problem is that the priors, of course, are defined in this parameter space, which changes with different parameterizations. So it's sort of arbitrary how you parameterize the model, which means it's very difficult to intuit about what the right prior parameters should be. And so, yeah, that makes it really difficult. And often there's this misunderstanding understanding when talking about priors is, they should be objective and they should be just very wide and not influence your data at all. I mean, then you don't need priors in the first place, right? So when we have priors and every analysis has subjectivity baked into it, we are just very disciplined of writing those assumptions into the model directly. But that also means that if you are in that iterative process and look at certain behaviors of your model, for example, that it produces these types of data sets that you would never expect to see in reality, it means that you do have prior information that you did not incorporate into the model, right? Otherwise, you couldn't evaluate that this thing that the model just produced is completely unreasonable. So that allows you then to completely, in the philosophical correctly domain of Bayesian statistics, to go back and change the prior so that the model behaves in a way according to your intuitions. And then, of course, you move to fit data, and then you see, it's also doing this weird thing because the sample is dropping into the parameter region, and I know that that is completely wrong and it doesn't even need to go there. Well, then you can change your prior to exclude that. So yeah, it is part of that iterative process, and that is totally fine to do and go back and revise your priors.
Yeah, exactly. As you said, you often know a lot actually about your problem before even seeing the data. I mean, for instance, if you're modeling heights, well, you know that people, when they are adult, they very rarely are below 1/2 of a meter, and they're very rarely above 3 meters. And I'm being weakly regularizing here, but you can already bake that knowledge into your priors, as you said. Yeah, also something that made me think about that when you were talking about problems that you get because of the sampler, maybe not because of the model, is standardizing predictors and outcome when possible. It can really, really help with sampling, especially in hierarchical models.
Yeah, that's also true. I have the dream that one day we don't need to do that and the samplers will just be fine even without that, just because it, again, adds more complexity. Like these transformations of your data are helpful, but again, they're just a crutch, right? We just do that because the samplers are not powerful or because the tools don't automatically do that for us. So for me, as a developer of these tools, I think about how can I automate that process and make it transparent so that the user just inputs non-standard data, and maybe that happens behind the scenes, but then the outputs and everything else gets transformed back so that you only see things in the space that you intuitively think about it.
Yeah, exactly. That would be awesome too. Maybe to wrap up on these kinds of model because I could talk about these for hours, because these models are quite hard to interpret. Because you have different levels, so the cluster level, the population level. So, of course, it means that you have often dozens or even hundreds or thousands of parameters. So it means the dimensions of your model are very big, very fast, and it can hurt understanding and interpretation of the model. So I'm wondering, how do you usually deal with these numerous dimensions in the models? And maybe to just take an example for listeners, I would say, for instance, if you were looking to model something at the scale of Paris, let's say that, well, for instance, right now I'm trying to model elections in Paris at the district level. So in Paris, you have 20 districts, and let's say you have 7 parties in each district. So you already have 20 parameters times 7. And then if you had the hierarchical level at the city level, you would add even 2 more parameters at least for a mean and standard deviation. So it gives you a lot of parameters and a lot of dimensions. And so how do you deal usually with these dimensions? Do you plot them? What's your workflow there?
Yeah, that's a great question. It actually links back to our discussion earlier, where, for example, Adrian Zelbold built this incredible model with like 40,000 parameters. Well, we could analyze some of them, but really we didn't care too much about individual parameters. I would always ask the question, well, why are you even building that model in the first place? What do you want to do with that? And often the answer is not because I want a posterior distribution over X. The answer is I want to predict an election. I want to find the subset of algorithms that I want to invest in. And that then turns it into a utility problem and moves you away from the complexity of the model and moves you into more really finding the best way to crystallize everything that the model has learned, so produce an output around that. So for example, in the election case, well, maybe you want to predict what the election result might be. And towards that goal, you could start to generate posterior predictive data, and that will directly inform you of, well, in 80% of these simulations, this candidate won, taking all the hierarchical structure and things that you just mentioned into account. But we don't care about that at that point, right? The model has already learned about it, and we tested and validated the model, but we don't care about each individual parameter, tracking each individual part of Paris. We only care about what that means for the problem that we care about, in this case, which candidate is going to win. Or maybe you are the candidate and you want to know, okay, what should I do? Which district should I focus my attention on to maximize my chances of winning that? That then gets us back to a Bayesian decision-making problem, right? Where we could, okay, well, let's simulate all different scenarios of how people would vote according to what the model has estimated. And then you could define an objective function and say, okay, how much time should I spend in each district in order to maximize my chances? Then, so that is an optimization problem. And you have forecasts of what might happen. You have your objective function. You plug that into an optimizer, and it will directly tell you the answer. This is exactly how you should allocate your time. That is really the realization that I have come to quite recently, actually, that, yeah, it's not about the parameters or the complexity or the posterior distributions. It's really about what do you want to do with it.
Yeah, that's very interesting. And it wrapped things up quite nicely with what you said about earlier, about decision making and so on, and cost functions. Okay, so that was really amazing, this part about the hierarchical models. And I'm really glad we got to cover that in depth in this episode, because it's a topic that often gets back in other episodes. And I've been saying for a long time that I want to do a whole episode about that. So I'm really glad. And again, I could talk about them for hours, but maybe let's try and expand our perspective a little and talk about Bayesian deep learning. I know it's a topic you like to explore, so maybe tell us why, and maybe tell us even what Bayesian deep learning is.
Right, yeah. So part of the reason that I got into it, and I think the field too, is that, well, everyone knows that deep learning is amazing and everyone's super excited about it. And Bayesians have the tendency to go like, oh, well, really what you guys are doing is just this type of regularization that you do is really just a Bayesian way of doing this. So we try to assimilate everything. And Bayesian deep learning is our most recent attempt of doing that with deep learning. Of course, this is mostly joking around. But so the idea is that we can gain a Bayesian perspective of these models and express them in a Bayesian framework. Well, one thing is we do see these very deep connections. So at the very simplest level, usually what you do if you have a neural network, you apply L2 regularization, quadratic regularization to your parameters. You want your weights to be small. You want to pull them towards zero. And that is equivalent to placing a normal prior on them, or maybe it's an L1 loss and prior according to that. Or maybe use dropout. And then there's another interpretation that dropout is just really prior on your weights. And that perspective often opens the door to other insights. So once you incorporate things that people have validated empirically and you understand them theoretically, you can make more progress by linking it to these other things and pushing the theory a little bit forward and then testing the results of that empirically and seeing that holds true. And for example, in the case of dropout, that worked. So Yaron did his PhD thesis on that. And one of the results was that people used to do dropout only during training. He realized that, well, actually, you also need to do dropout during prediction, and then you get better results. So that's one neat example where having these links actually helps you in building better models. A lot of the things that I initially was interested in and still am is where we can place more structured priors on these weights. The examples in my blog post, for example, are, well, what if you have a classification problem and, as is common in quantitative finance, things are changing. So classification problem that you're trying to solve will look similar, but not the same 1 month from now. Then you can apply all the machinery in Bayesian statistics that you have for modeling time series. For example, you can place a Gaussian process on your weights and allow them to change over time and estimate how the right parameters for the right time. And that is one blog post that I did on that. We talked a lot about hierarchical models, but you could also build a hierarchical neural network model where each neural network model would be the best classifier for a certain cluster. If you know that there are multiple clusters and they share similarities but also differences, well, that's, again, just a very natural hierarchical model. In general, the insight is that, yeah, we can expand these priors and we often don't really care too much about that. Also, interesting links back to our discussion earlier where it's not really about the parameters. So the parameterization of these models often is somewhat arbitrary and thus are the priors. But the idea is that by placing priors in weight space, those transform or translate to priors in function space. So what are the functions that this type of neural network model can fit. And by being more clever about that, you can hopefully enhance, and there are some good examples where that is already happening, you can enhance these models by placing these more clever, more structured priors on your models, on your deep neural networks. Yeah, so that is, I think, one of the reasons why people are interested in them. I would argue the very strong example where it just is way better than anything else and it becomes obvious that this is the right approach. For me, that proof is still out there. So yeah, it looks promising, but I wouldn't say we completely nailed it yet.
Yeah, that's very interesting. As you said, all those things you mentioned look really promising too. And yeah, I think people will be interesting to learn more about it in your blog post because we're getting short on time, so we can't really detail everything that you said there, but that looks really nice. And actually, what's your technical stack when you do that? Do you still rely on tools like PyMC or Stan, or do you switch to other packages that help you do that?
So for those blog posts, I use PyMC 3. But yeah, I do want to add that for me, these were really just fun explorations. They weren't fast or scalable enough to really, I think, be used for serious problems. It's really just like exploration, but not application, for me at least. Definitely for Bayesian deep learning, I think better tools exist now that really build on more solid foundation, more scalable foundation. So TensorFlow probability and also PyMC4, which will be built on that. That is a great tool. Pyro, these often have demonstrated to be able to scale really well to really big networks. So the networks that I built were really just small and they were complex in the structure, but still the number of parameters and the level of depth they had were really limited. And the reason for that is, well, the scalability of the variational inference or the sampling. So solving that is a challenge. And I think some of these newer tools do a better job. And for the reason that they also place a lot of focus on that. So it's an explicit case that they optimize for, and PyMC3 is not and does not plan to optimize for this particular case.
Yeah, and as long as you're talking about PyMC4, let's dive in a little into that because as Chris Vansbeck said in episode 2, development is actively underway. So where are you guys at? Let's do some check there about the development of this new version of PyMC.
Well, okay, so first the current status is that we released an alpha version not too long ago. That is highly experimental and probably broken in many ways and will break in many ways. So it's not fit for production use, but it is functional for a lot of the things that you actually can already do with PyMC 3 already. So it was really a positive surprise when we made the decision to build on TensorFlow probability. We saw that already provided a lot of the building blocks, but it's really a low-level library. So we thought, well, it's great to take these low-level building blocks and build it into something that is focused on being easy to use and have great user experience. And I was positively surprised by how quickly we were able to assemble these pieces and get something that was similar in functionality to PyMC 3 rather quickly. So yeah, it is functional and there's the nut sampler. The current limitations are related to speed. So that seems to be a general problem of TensorFlow, that specifically with the nut sampler, that if you have smaller to mid-sized models, it is more built towards like really large scale computations. So PyMC 3 will still be faster in many ways, but I hope that that will be solved with more time. But also one thing I come to appreciate with Theano is actually the fact that it was abandoned and discontinued might not be the worst thing in the world, because what it means is that it's stable. And also, as we announced, is we're going to take over maintenance. So we will just make sure that it keeps running. But it's really an amazing library. I'm really bummed that they stopped developing it because, well, one thing is it has like 10 years of development behind it to really make it robust and good at the thing that it wants to do. And the thing that it wants to do is build static graphs. And for Bayesian models, static graphs are completely fine. We don't need dynamic graphs that just allow us to do all kinds of crazy things like changing dimensionality while sampling. We don't care about that use case. So a lot of the current frameworks, including TensorFlow, but also PyTorch, are optimized for a different use case than what we actually need. So with PyMC4, we have that problem where we need to apply all these tricks in order to handle the dynamic graph, which we didn't need to do with PyMC3. So yeah, I come back to appreciating the simplicity and directness and speed of PyMC3 and also Theano. So I think it will continue to serve us well. And I wouldn't make strong predictions that in some time time frame that I will start telling people, oh, just forget about PyMC 3, start using PyMC 4. Really too early to say where this will lead. It looks promising, it's functional, but PyMC 3, I think, is still at and where it's going to be at for quite some time.
Yeah, that's interesting to know. Maybe you will have kind of different use cases where it would be more interesting to use PyMC 3 than 4 or vice versa.
Yeah, exactly. The field is moving so fast that it's very hard to predict, but your point is a good one, also related to what we were saying before about Bayesian deep learning. So that is a use case that we not optimizing for in PyMC 3, but if we get that for free because TensorFlow probability cares about it and that translates through to PyMC 4, well, that could be really interesting. So in general, under that umbrella term of really big models. So if we're allowed to now build models not just with 40,000 parameters, but maybe 400,000 or millions of parameters, what does that do? Does that open any new doors? Are those even types of models that we want to build going to be useful? I don't know, but it could be really interesting.
Okay, Thomas, we're getting short on time. So before letting you go, I'm going to ask you the 2 questions I ask every guest at the end of the show. So the first one is, if you had unlimited time and resources, which problem would you try to solve?
That's a good one. I would say probably climate change and related to nuclear energy, which I don't know too much about it, but from my own understanding, it seems that is really where we have the best track record in terms of scalability and cost and safety that could really be really meaningful impact. Not saying to take any away from other techniques that we're working on towards now, but I think being able to hedge our risk in terms of coming up with a stable energy infrastructure, I think nuclear is wrongly dismissed.
Yeah, that's interesting to hear. Actually, that's the answer. Junpeng Lao answered exactly the same thing for this question. Maybe you guys can work together and you can also come to France because we have a lot of active research on this topic.
Yeah, exactly. Like France is my favorite example for how well this actually can work.
Yeah, exactly. It's a very interesting use case.
Yeah. And Germany is a great example of how it could not work. It's good contrast.
Exactly. The second question is if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
I would have to pick Richard Feynman. He seems to be the most badass of all the guys out there. I don't know if this story is true, but a friend of mine told it to me. And I do know that parts of it are definitely true. So he liked to do his research in strip clubs. That is just like where he could be by himself and like have some nice distraction. So he would just hang out in strip clubs and do his physics proofs. And then the owner of the strip club got into some legal troubles and there was character witness required, and no one would be willing to go in front of a judge and be like the character witness for this person. But Richard Feynman was like, oh yeah, sure, I'll recommend this guy. He's an upstanding citizen. So yeah, again, I don't know if that is actually validated or just myth. He seemed also for other reasons just a really cool, chill guy, and I enjoy his perspectives on communication skills on many things.
Yeah, that's definitely a good pick. I love it. Well, Thomas, it was really great talking with you. I hope we help people better understand, fit, and interpret hierarchical models. They really remind me of a superpower, but you know what comes with great power, right? I also wanted to thank you for the amazing work you and the whole PyMC team do. And I'm sure I'm not the only one to be grateful. As usual, I put resources and a link to your website in the show notes for those who want to dig deeper. Thank you again, Thomas, for taking the time and being on this show.
Oh yeah, thank you so much for having me. I had a great time.
Thanks.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher, and visit learnbayesstats.anvil.app for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayesstats.anvil.app. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Mega Ram. Check out his awesome work at bababrinkman.com. I'm your host, Alex Endora. You can follow me on Twitter at Alex_Endora, like the country. Thanks so much for listening. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.